Hello everyone, my name is Balázs Vas and I am an assistant lecturer at the Budapest University of Technology and Economics, Hungary. And I'm now going to present our paper titled Programmable Packet Scheduling with SP-PIFO, Theory, Algorithms, and Evaluation. Let me share my screen. My co-authors are Csaba Sarkadi and Gábor Rétvári from the same university, and I am also a member of the EIT Digital Industrial Doctoral School. So some words on the programmable packet scheduling. As programmable switches emerged, the possibility of refining on-the-fly the packet scheduling was opened up. This can be done using a high-level programming language, for example, P4, and the push-in first-out PIFO queue was the first hardware abstraction that enabled tweakable packet scheduling, where the packets are sorted and dequeued by their rank and associated number, integer. But sadly, there is no hardware realization for this one up to this time. So as far as so the FIFO queue works like every packet what goes in first, it goes out first. So and this order is maintained. In the PIFO, however, the packets are sorted by their rank. For example, this packet 2 rank just goes in the middle of the queue, and the packets are then dequeued according to their rank in ascending order. So the SP-PIFO was proposed some 2 years ago. The strict priority PIFO, that is a PIFO approximation. It maintains a set of strict priority queues, a set of FIFOs, and it freely adapts the mapping of ranks to queues with the aim of minimizing the inversions committed. For example, if rank 1 to 3 packets goes to the first queue and ranks 4 and 5 packets goes to the second queue, and this first queue is dequeued first, then we can see that in this case we have some inversions, but if the rank 3 packets went to the second queue, we had no inversions. So there is something to optimize here, and we are about to investigate it. The mapping strategy offered in the SP-PIFO paper was called the push-up push-down algorithm, or PUPD. So the mapping goes like the queue bounds are scanned bottom to up, and the packets are enqueued in the queue if its rank is greater or equal than the queue bound. And so, for example, in this toy example, the packet with rank 4 arrives, 4 is bigger or equal than 0, so it will be enqueued to this queue. Here, a push-up happens, and the queue bound will be set to 4, to the rank of this packet. Then let's assume that rank 3 packet arrives. It will go to this first queue, and the queue bound of this queue will be set to 3. And then let's assume that the packet with rank 1 arrives. Here, something different has to happen. This packet will be enqueued in this first queue, but all the queue bounds will be decreased by the difference of these two numbers. This is called a push down, and we will end up with something like this. The queue bounds are decreased by 2, and this packet is enqueued here. So this is push up, push down in a nutshell. No one really analyzed the competitiveness of it, so we do it here. So first, the deterministic competitive ratio of the push-up, push-down is presented. So we will use a simplified error metric, which in case of a deterministic packet sequence S is something like this. It's really just writing down that if we have one of the strict priority queues, we check the adjacent packets included there, and if the latter packet has a lower rank than the former one, we count it as an inversion. So we have here an inversion, and here another inversion is about to happen with packets with rank 2 and 5. Okay, what is a competitive ratio of an online algorithm? So it is just the maximum proportion of the cost that an online algorithm makes, and versus the offline optimum on any input, on an arbitrary input. And so we have a theorem that the competitive ratio of the push-up push-down is at least as much as many queues we have. The number of queues will be denoted by n here. So it holds even if we have only the number of queues plus 1 ranks. So the push-up push-down is optimal if we have at most as many ranks as many queues we have, because then every queue has to deal with at most 1 ranking. Everything is simple. But even if we have the queue number plus 1 ranks, with more queues, the push-up push-down gets further from the optimum. The proof is in the paper. I just want to give a taste of it. We make this packet sequences input that we start with packets with rank n plus 1, the queue number plus 1. Then we go down to 1 and then back to n, and we can repeat this one as many times as we want, L times. Then in all the queues of the push-up push-down in qi, there will be packets with rank I plus 1 and packets with rank I, and in a ever-changing order. So we will have in each queue L inversions in case of push-up push-down. In case of the offline algorithm, we say that let's enqueue packets with rank and packet with ranks 1 and 2 to Q1, and then for all the other queues, we say that QI have to deal with only the packets with rank rank I plus 1. So here we have L inversions in the first queue and none in the others. So this proportion of the inversions is just n as needed. Okay, so what's about the randomized competitive ratio of the push-up push-down? Because we cannot control the exact sequence of packets which arrives to an SP-PIFO system. So a simplified stochastic error metric is with a stationary distribution of packet ranks P is just the expected number of inversions, which can be formalized with something like this one. And our theorem is that in this case also the randomized competitive ratio of the push-up push-down is at least as big as the number of queues, even if the number of ranks is just n plus 1, and the proof is similar to the proof of the offline version. We make the push-up push-down commit 1 inversion in all the queues, while an offline algorithm makes just 1 inversion in 1 queue. Okay, so time to speak about some positive results. The offline stochastic optimum can be computed in polynomial time. So what we mean on that if we know the packet rank distribution P, the optimal static queue bounds can be calculated in the order of k squared times n, where n is the number of queues and k is the number of ranks. Yes, if the queue bound of the ith queue is qi, then qi gets ranks qi to qi plus 1 minus 1. Let pi denote the probability of the next rank being I, and capital Pi is just the probability that the next enqueued packet will go to qi. Then the probability of the next packet causing an inversion in qi can be calculated. It is something like this one. And we will use a shortest path finder algorithm on a graph to compute the optimal solution, the optimal queue bounds. So the graph is the following. for each rank, there is a node in the graph, and we have an imaginary helper node at the end. We will make a full DAG, a full directed acyclic graph, and the cost of the arcs will be this expression stated here. And in case of any other cost, our algorithm would work. So, and there is an observation that the nodes of a shortest V1, Vk plus 1 pass of at most n arcs are just encoding the Q bounds of an optimal static solution. And this can be computed by a slightly modified Bellman-Ford algorithm, as explained in the paper. So this is, in this example, we have two Qs. This red path has two arcs. The maximal, we have 4 ranks, and the Q bounds are 1 and 3 respectively. Yes, we have some issues with this algorithm. It cannot be implemented in hardware switches, and it is offline. We need an online algorithm which uses much less space, because in hardware switches there is not enough space to store the probability of arriving really many ranks, possibly very many ranks. So we need something simple here. We will say that we just store only the load pi on each Q. We will just minimize the maximum load on a Q, so we will even out that one. And for now, we say that the time is continuous, the ranks are arriving continuously, the ranks are continuous, and everything is continuous. We will rediscretize this one. But here, the optimal solution would look like something like this. Yes, the load on each Q should be equal, and the load is just the sum, the sum of the probabilities, roughly saying, between the respective Q bounds. So the optimization of this setting is inspired by physics. If springs were attached serially, so the rank intervals are as springs which are attached to its upper and to their upper and lower bounds. The Q bound Q1 is nailed down to 0, and the imaginary Q bound Qn+1 is nailed down and in the infinity. And the bigger is the load on the load on Qi, the more it pulls together its Q bounds. and we can see that this algorithm is converging to its optimum quite fast. In case of here a uniform distribution, and here in case of an exponential distribution. Okay, so we need to fix here some stuff because some values are not continuous in the real life, and also the distribution of packet ranks is needed to be learned online. So for this one, we use the exponential weighted moving average, which is implementable in P4. So the amortized number of packets is learned this way, where IIT is just the indicator variable that the packet arriving at time t is included in Qi, and alpha is just the speed of forgetting. Yeah, the Q bounds need to be integers. We say that we still optimize on the continuously relaxed Q bounds, but then we round them up to get the actual Q bounds. Inversions in the Q bounds have to be prevented, so it is engraved in the program that we maintain the ascending order of the Q bounds. And this program should be PIFO compatible because all the resource usages are similar to the resource usages of SP-PIFO or AIFO. And this is just a pseudocode of our Spring heuristic. Is really straightforward. We maintain the Q bounds, the linearly relaxed Q bounds, the amortized number of packets included in each queue for each arriving packet. Basically, this is that. So in our evaluation results, the simulation settings, we recycled the NetBench simulator of the SP-PIFO paper. In addition to PUPD and Spring, we tested also the greedy, which is proposed in SP-PIFO. And in case of stationary rank distributions, it converges to the optimal bounds, but sadly, it's not implementable in nowadays switches. We used 8 queues in the simulations, and for Spring alpha was 0.01, and we used greedy with the basic parameters. We used the same rank distributions as the SP-PIFO paper, and the measurements were configured with a 1 second limit on the simulated runtimes. It resulted in around 1 million packets. We can see that the Spring made up to more than 2 times less inversions that the push-up push-down made. The Spring seems better than the greedy. Sometimes the greedy outperformed the Spring. It really depended on the rate of adaptation of the Q bounds to the optimal Q bounds. We also checked the sum of rank differences where the Spring was consistently better than the push-up push-down, with the push-up push-down committing up to 9 times as many total inversion size as the Spring. Well, the Spring seems a little bit better than the greedy, but here things are sometimes the greedy outperforms the Spring too. For example, in this exponential distribution. But our conclusion is that the Spring really outperforms the push-up push-down and compares to the greedy. And this makes the Spring a good Q-bound adaptation algorithm. And that's all. This concludes my talk. I'm happy to take questions. Thank you, everyone.